Hi everyone, today we're covering 5.9, the steady state approximation. Now in the last video we talked about writing a plausible mechanism for a slow step, assuming that it's first. But what happens if our first step, or initial step, is fast? We have to treat it a little bit differently and use what's known as the steady state approximation. And so if the slowest step of the mechanism always determines the reaction rate, if this first step is fast, we have to approximate the reaction rate. And you'll see on the next slide why we need to do this. But we generally follow this scheme written down here. First, we'll write the overall reaction. Then we'll write the rate loss for the slow step and both of the preceding fast steps. You'll see what I mean on the next slide. The fast step, we can assume that this is at equilibrium. And so it should have a forward reaction that's equal to the rate of the reverse. And so what you do is you set the rate of the forward and the reverse equal to each other, and you can solve for an intermediate. At this point, you can substitute using just basic algebra, and then solve for the slow step of the reaction without any intermediates. And we're going to do an example of that right now. So let's take these two reactions here. We have NO plus NO makes N2O2. This step is first, and it's at equilibrium. And so the forward reaction has a rate constant of K1. The reverse is the exact same thing. It's just you flip it since you're going the reverse reaction. You have a second step, which is N2O2 plus Br2 with a new rate constant, K2, makes NOBr. And this is a slow reaction. If we take the overall reaction here, we add these two together, we end up getting 2NO gas plus Br2 on the left side. Our N2O2s cancel out on each side. And this will make 2NOBr gas. This is overall. Now, we always estimate, we predict the rate law from the slow step. We should always do that. And so we predict that the rate law for this reaction should be the following. Rate equals K2, because that's the rate constant for the slow step, times the concentration of N2O2 times the concentration of Br2. And what we notice here is a problem. We have an intermediate in the rate law, and rate laws cannot have intermediates. And so we need to rewrite this using the fast step, because we cannot have this rate law. This is a completely invalid rate law because it has that intermediate. And so the first thing we should do is write the rate of the forward and reverse reactions of that fast step. Again, we always just do the rate constant times the concentration of reactants. So for the forward reaction, it's K1 times NO squared, because I have two of them. And for the reverse reaction, it's rate equals K minus 1 times N2O2. Now remember the definition of equilibrium. Equilibrium means rate forward equals rate reverse. And so I can set these two equal to each other. So step 2 here, I just set each of the rates equal to each other. So K1 times NO squared is equal to K minus 1 times N2O2. And here my goal is to isolate N2O2. And so we just have to do some basic algebra. We find the concentration of N2O2 is equal to K1 divided by K minus 1 times the concentration of NO squared. And then now I can plug this back in to my rate law from the slow step. And so step 3 is to just plug back in. My rate is now equal to K2 times K1 divided by K minus 1. I typically like to put all the K's together. Then the concentrations, and it'll be concentration of NO squared times concentration of Br. Now to make things pretty, I can just define that K2 times K1 over K minus 1 is just equal to the rate constant K. And so now I get that the rate of this overall reaction we predict is K times concentration of NO squared times concentration of Br. And this is the new predicted rate. And so this steady state is called the steady state approximation. You use this when the first step is fast, and the second step is slow. Otherwise, you'll use what we saw in 5.8. All right, so let's work through one more example together. In this one, we have NO2 plus F2 is in equilibrium with NO2F2. Then we have that NO2F2 reacting to make NO2F and F. That is our slow step. And so our rate will be written from this one. And then we have a rate afterwards, which is F plus NO2 makes NO2F. So before anything, let's define all of our rate constants. For the first step, we'll call this K1. We'll call the reverse K minus 1. For step 2, we'll call this K2. And for step 3, we'll call it K3. And so when we're looking at this, we have to write our mechanism from the slow step, or rate law from the slow step. So rate is equal to K2 times the concentration of NO2 F2. Of course, if we look, NO2F2 shows up here and here. And so in our overall mechanism, this will end up not showing up in the overall reaction. And so NO2F2 is an intermediate. And so, of course, we need to make the rate law without NO2F2 in it. So we use the fast step from before. We find the rate of forward is just K1 times NO2 times F2. And the rate of reverse is equal to K minus 1 times NO2 F2. We set them equal to each other, just like we did in the last example. K1, concentration of NO2 times F2 equals K minus 1, concentration of NO2 F2. We solve for NO2 F2. It looks exactly like the last example. Concentration NO2 F2 is equal to K1 divided by K minus 1 times NO2 times F2. And then finally, all we need to do is plug in to our original rate law. Rate equals, we'll put all the k's together, K1, K2 over K minus 1 times, we have in our original mechanism, it's just NO2F2, and so that is just all of this together. And so NO2 times concentration of F2. We can make all the K's just equal K, and we have NO2 times F2. And if we look at our answer choices here, that is answer choice A. And so all of these proceed pretty much the same. You solve for the concentration of the intermediate, and then you plug into your original rate law. We'll do more practice in class, but for now, that's all. Thanks, guys.